Start it. Okay, start the recording, and then, as I mentioned, so we will skip different part and then talk about the black hole. I think black hole. Okay, and then of course we will connect in string theory because this is string theory course. How many of you guys heard of the okay, how many of you guys learn about Hawking radiation? So only two of you guys. Okay, how many of you guys learn about Kerr black hole? Oh, okay. Oh, you guys, where did you learn Kerr black hole and GR? Huh? Okay, so you guys know about Kerr black hole. How about rational North-Star black hole? Okay, no. Okay. 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 So around the 70s. So actually, Penrose got a Nobel Prize due to the theorem of singularity. Last year? Yeah. Last year, right? So that's I think late 60s, and the 70s. Lots of development has been made by many people, including Hawking, Bekenstein, and also how to say Carter Hawking, and then who was that? Bodin Carter Hawking. Actually, Bodin is a really brilliant guy. Actually, he's very bright. Sorry, I should have missed. Yeah, Bodin Carter Hawking made a black hole thermodynamics, and finally Hawking found a Hawking radiation. And also that leads to information paradox. And then many people think about this black hole information paradox. And then after the Polchinski interest, deep brain, mainly Strominger and also Madasena, it also made lots of contribution to the black hole physics in string theory. And then finally, Strominger, Vafa gives some microscopic understanding of Hawking entropy and so on, as you might have heard of it. So today we will cover this exciting part of the string theory. Yeah. So before then, let's start talking about the black hole. So let's start with the Einstein-Maxwell action. So 16 pi in Maxwell action, Einstein-Maxwell action. So G of 1 over G R F nu. This is familiar action in the 4 dimension. And G is Newton constant, and then so we will consider the solution, a black hole solution. And many people, so without this one first, 1 year after the Einstein's work, Schwartz found the spherical statistic, the black hole, and then including this one, this Maxwell action, rational Nordstrom found the solution. So that's what we will review first. First, let's assume. So this is the Einstein Maxwell action. Okay, and then but first, so we will consider Schwarzschild black hole. Black hole that is indeed, so first we assume f equal to 0, f mu nu equal to 0. There's no electromagnetic gauge field, magnetic field. Then, oh, there's a typo already. So, equation motion is this guy, as you're familiar. So there's a typo in the lecture note. And we assume a spherically symmetric and static solution. And this is if mu 0 is, you already know, spherically symmetric, and then also static solution. And then the metric is written as follows: minus 1 over 2gm over r d square plus 1 minus 2gm over r inverse dr square, and then sphere metric. Okay. So this is a Schwarzschild black hole. So this is of course time, and the r is the radius. Okay. And of course, so how many of you guys have learned about the Schwarzschild black hole? So 1, 2, 3, 4, 5. Okay. So where did you learn? GR course. So Eden has taught this one. Not Eden. Who taught this GR? Maybe Cosmo. Antonino, Cosmo. Good. So then I don't need to spend so much time on this. Everybody knows. So as you can easily see, when R is equal to 2gm, something strange will happen. So GRR, so the upper spectrum. So if you take GRR, it becomes 0. Okay. So this is called event horizon. And once you enter that, so of course you know G is Newton constant. So then radius is proportional to radius. Radius is proportional to the mass of the black hole. Okay? And then as you enter the black hole, you cannot come back. Okay? And then it's a bit cheating, but so let's do the following thing. So if you take they go to some wick rotation. So t is equal to minus I t Euclidean time. Then and also we set r minus 2gm to look at the solution in a black hole. X square plus over 8. GM, okay, and then around the metric, Ukrainian metric, it becomes like this way, kappa of x. So it's a good exercise to move that metric to here by the change of variable plus dx square plus 1 over 4 kappa square d omega square around the event horizon. Okay, which means the R is near this one, 2gm. Okay. And where copper is important quantity, which is called the surface gravity. So copper is indeed 1/4gm, which is called surface gravity. And then, so I think, so you guys doing the homework maybe? Then next one. So not this this week's homework. Next homework is the last in that case. And then the homework, you have to show that this is the indeed the acceleration. Acceleration of static particle near the horizon, measured at the infinity, spatial infinity. So in other words, so there's a black hole on the horizon is r is equal to 2gm. And sometimes when people say black hole, people think the singularity is a black hole, but including all the event horizon, that's called a black hole. Anyway, inside of event horizon is called black hole, not only singularity. And then there's a spatial infinity. Let's consider this a spatial infinity, and put some particle here near horizon, and put the string, just string. Just let's get on experiment. Then the observer at the infinity feel the force because this particle is just is attracted by black hole, and you can measure the force at the infinity so that you can measure the acceleration. And this is exactly the kappa you will measure. This is exactly the acceleration, or which is called surface gravity, which is 1/4gm. This is next homework, and the last homework. And then the first part of metric. So if you look at this metric around here, you can see that so if you do this, it's kind of cheating, but anyway, so if you go to the Ukrainian metric and look at the near horizon, then TE is identified. If you do the following identification, you can do the following identification. If you do the following identification, this becomes really polar coordinate. Okay. So, and also if you consider the relation between Euclidean periodicity and temperature, so if you consider the space-time on S1 cross R3 and the radius R, okay, this R can be understood as the 1/temperature. In the Euclidean block, so if you consider the E to the minus in statical mechanics, you have the weight, the Boltzmann weight E to T, right? E temperature in Boltzmann weight is E over T. Okay, E over T. Yeah, thank you very much. Boltzmann weight is E to the minus E over T. Can be obtained by weak rotation of E to the I E Hamilton T. It's just weak rotation to get this one. So that this radius can be understood 1/temperature. Okay, Boltzmann weight. So this cup. So therefore, this periodicity identification, it's very heuristic argument, can be understood as the temperature of the can be related to the temperature, which which is nowadays called the Hawking temperature. It's very heuristic. 8, 5. I just introduce all the constant. H bar is Planck constant, G is the Newton constant, and then this is called nowadays called Hawking temperature. So if you do the weak rotation metric and then look at the coordinate as a time, the period on the time direction, then somehow the Hawking temperature pop-ups. So this is not original way to define this Hawking temperature, but a heuristic. This is the one way, easiest way to see the temperature of black hole. So important thing is that this now, so you have a H bar and the G, Newton constant, and the Planck constant meet each other here, and the temperature is proportional to 1 over black hole mass. So if the black hole becomes smaller and smaller, and then temperature becomes hotter and hotter, and then of the black hole. Okay. So already this is an instant black hole can be treated as some thermodynamic object. Okay, so this is the Schwarzschild black hole, and now so I will talk about the Reisman Northstone. So the reason why I included how to say the I think Northern Strong. I don't know who black hole. I think Northern European people. I don't know. Looks like a Swedish name, but I don't know where they come from. So now, the reason why I include this one is that the black hole has is characterized 3 quantities. What are the 3 quantities? Mass and charge. Okay. So good. So black hole has a 3. Its parameters 3 quantities: mass, charge, and angular momentum. And here, I just assume J equals 0, and then Lysen-Olsson has the mass and charge. Okay? Charge in terms of the gauge field. So then, again we assume the spherically symmetric and static. Spherically symmetric and static. Static means the metric is independent of time t. Okay? Of course, there is a dt square direction. Where was it? Dt square direction, but all the components are independent of time t. Okay, so then the metric can be written as follows: minus 1 minus 2gm over r, and then plus gq square over r square, gq square, and then the same piece but meters, and the r square, and plus this the usual component. It's very simple enough. So you just add this charge component, charge term, to the Schwarzschild black hole. Sorry. Oh, my chokehold is no longer working. So where so this is metric, and then the field strength is only this component is non-trivial, Q over R squared. So in other words, you only have electric field, no magnetic field. So the solution is called Reisman-Olsson black hole parameter charge so let's erase this part because we already seen this one. So then again, so GRR equal to 0 is indeed event horizon, but now you have a two solution, GM plus minus square root GM square minus G square. And then plus will correspond to R plus is correspond to outer horizon, and also R minus is called inner horizon. So you have a two horizon. You have, and then of course the black hole is the inside is inside R plus. Okay. So the area of black hole is indeed here. Areas of black holes. Okay. So the Schwarzschild area of black holes A is equal to 2 pi R square, right? R square of Schwarzschild black hole. And here, so not 2 pi, 4 pi. Sorry. Schwarzschild. So this is also same area. The black hole is 4 pi R plus square. Okay. So that's the. The Hawking temperature, one can just also do the same exercise. Then Hawking temperature will be modified as follows. Maybe it's better not to erase here. So let's. So the Hawking temperature is TH is equal to GM square minus GQ square, and then divided by 2 pi G, and then GM plus square root GM square minus G square. So now it depends on charge Q and N. You can do the same exercise. And as you can easily see, so from here, one can get some insight about the physical insight. Now, of course, temperature has to be greater than 0. So which means greater than or equal. So which means the numerator here, if you look at the numerator here, one can conclude that the GM square has to be greater than or equal to GQ square. Okay? So, and then, so GM square and Q square, this has to be obeyed. So you cannot arbitrarily increase sorry. Okay, so I mean, just keeping charge Q, you cannot arbitrarily decrease the mass of the black hole. You have a bound, and if the bound saturates, it's called the extreme of black hole. So when GM square is equal to Q square, then temperature is equal to 0. Okay, and then this is called. Did I call it extremum? My note? Oh yeah. So this is a black hole is called extremum. So it's very so if you add a charge on a black hole, yeah, if you keep increasing the charge and if it hits this bound, the temperature becomes 0. And then this looked like, I didn't introduce, but this is related to, I didn't introduce, it's called BPS. So BPS one is indeed, this BPS means the often mass of the particle is greater than so-called central charge. It's very look like this. Maybe you can just M square is the central charge of the particle. So this is the related to BPS. I will explain a little bit later. Okay, so in this case, of course, if you look at this on this part is already become zero. So therefore, for external black hole, our plus is inner and outer horizon coincide. Okay, so that's the extremal case. Okay, and then now, as I mentioned, you have a three quantity, and we just put the j equal to 0. And next thing is what we can do is the add angular momentum. Oh, by the way, did I write? I think I wrote, right? So at the beginning of this section, I refer to the lecture note. Of course, so you in the homework, this to derive this Hawking temperature. Not Hawking temperature. Sorry, the surface gravity as acceleration measured at infinity. I mean, this one is written indeed. So this is a good book by this one. Walt book is also good reference. And also, but the black hole thermodynamics Townsend book is very nice. Townsend lecture. I think it's only like 70 pages. I already forgot. When I was a student, I read this. Huh? 140 pages. Okay. Maybe I think I made a double page printing. That's why. Anyway, but it's concise. So Townsend has a very wonderful lecture note about this one. So if you're interested, you can just take a look at this. You can read and then. Yeah, my lecture notes is, as you can easily see, just a really condensed version of this Townsend. Okay. Okay, I'm not going to write down everything, but so if you just add the M, Q, and J, okay, and the stationary, okay, stationary solution. Stationary solution, which means that the of course, it's already put the angular momentum. You cannot spherical symmetric. Okay, so angular momentum means you just put the axis and then you just put the rotation around this axis. No longer spherical symmetry is broken. So stationary means the J is constant. J is constant as the time goes. And then I'm not going to write down everything. It's complicated. And then everything to write down everything. dt square. dt square. And then, which is written in my lecture note, my square theta. The important thing here is this one. And then r square plus a square minus delta sigma and dt. So so far, I already erased the short-seed black hole metric, but oh my goodness, here. Even as you can see from rational non-storms metric, you only have how to say diagonal. So if you don't turn on J, the metric can be diagonalized dt square, dr square, and then the spherical metric. On the other hand, if you turn on the J, you cannot diagonal, and the metric is no longer diagonal. dt, d phi component will show up. So this is the most important feature of the metric once you turn on the, and then I mean a bunch of anyway, sigma over delta dr square, and then spherical metric. Just some deformation of spherical metric plus sigma z square, where the I mean you can see I'm not gonna write down everything. Sigma is r square plus a square cosine square theta, and delta delta is r square minus 2m r plus a square plus e square, and it's a bit complicated, but important things is A depends on J angular momentum. So this off-diagonal component always depends on the angular momentum. This is the most important thing. And also, you need to turn on both electric charge and the magnetic charge. This is the most general solution. So this E appear here depends on Q and P, electric charge and magnetic charge. So more precisely, electromagnetic charge. Okay. So this is the the most generic stationary solution, and that is called Kerr-Newman. Kerr-Newman black hole. I think Newman. Indeed, Kerr black hole is the first found. Kerr black hole is found without introducing magnetic charge, just only turn on M and J. And the Newman found the most generic solution for Einstein-Maxwell action by introducing Q and P. And then in lecture note, I'm not going to write down. Of course, since you have a Q and P, electric charge and magnetic charge, you have to turn on the gauge field mu, which depends on some function and the Q and P, which I'm not going to write. It's a one form, so okay, gauge field one form. I'm not going to write down, so it's written in my lecture notes. So the gauge field needs to turn on. Gauge field, gauge one form should be turned on. So that depends on electric charge and magnetic charge. That's the most generic solution for stationary black hole. Okay, so this is some crash course of the black hole solution. Huh? Yeah, yes, go ahead.
Is there any physical meaning of this E? It's looking at some
Good question. I have never thought about it. Maybe I thought about it.
Sorry, could you repeat the question?
So if you look at the E, so E square is equal to Q square plus P square is a Pythagorean theorem. So I think what he meant is just if you go to 计算三角形 P right triangle, they satisfy this relation. So is there any what is this physical meaning E? That's his question. I never thought about any. But this quantity often appear even string theory, Q square and P square.
And sometimes I think there's some similar relation in QFT about the coping constant between the
Yeah, because this is the invariant under S duality or electromagnetic duality. So if you change, how to say, electromagnetic duality, of course, swap in Q and P. Okay? But this E is the invariant under the electromagnetic duality. So in that sense, this is most natural quantity, but I don't have any other insight and an better answer at this moment. Okay. Right triangle. Yesterday I learned how to call in Chinese. Yeah. Okay, so this is the most, and then, so which year? The published in 1973, I think. 1917. As I mentioned, so you can just extract some temperature out of black hole. So you can just body
I think you write this Q equals P to the M0, it should be A in electrons.
Where?
This should be A equals to G on Q.
No, I wrote this is A. So my handwriting is horrible. It's not. I don't mean to. It's Q. My handwriting is horrible. Sorry. Okay. So as I mentioned, so the body quantum Hawking noticed that the MJQ is looks like the three laws of thermodynamics, and then even though nobody expected before the body quantum Hawking, so this is the black hole is the thermal dynamic quantity, so that they have to obey the thermodynamic law, the basic law in thermodynamics, Zillow's law. Zillow's law of thermodynamics is the temperature is, so the temperature T is constant in the constant throughout the body. The body at throughout the body. Yeah, I'm not gonna throughout the body in some in some equilibrium. Oh my goodness, equilibrium. Yeah. So this is the equivalent to the surface gravity. So as I mentioned, the Hawking temperature is essentially 1 over kappa. Surface gravity. Kappa is constant along the is constant in the at the event horizon. At the horizon of the stationary black hole or of stationary black hole. So this is resemblance between zeroth law and the first law is the very simple. Energy is conserved. And then change of energy depends on the, of course, the you already learned in the statistical mechanics or some dynamics. Which one? I don't know. The first law is energy is conserved. And the change in energy in the thermodynamics object is dq plus omega dj. Okay. Where mu is chemical constant. And then chemical constant of charge omega and mu are chemical constant, and this is just can be written is the change of the mass of the black hole can be understood as kappa 8 pi g and dA. So the now area of the black hole can be compared to the entropy. Okay, already entropy of the thermodynamic object, and then the rest of the same. dq plus omega dg. So the mass of black hole, the change of mass of a black hole is compensated by a change of area, change of the charge, and change of angular momentum. In the case of black hole, so all the three quantities that appear to characterize the black hole appear already in its thermodynamics. First law of thermodynamics. Okay, and as you can easily see, this temperature, Hawking temperature, is I already introduced. Oh, sorry. Temperature is not one over kappa. Sorry, temperature is proportional kappa, and then this is indeed. So I just mentioned that 8 over kappa, and then 2 pi, and then I don't know why I didn't make. Sorry, actually, I don't know why I normalized 1 over 8 pi g, to be honest. I was thinking about. Oh, I see. So okay. So since now I understand. Since temperature is kappa over 2 pi, so that the relation between entropy and the area has to be normalized by some 4 pi g. Okay. So therefore, eventually we will see S is equal to area of 4 pi and some g and constant c and h bar. This 4 pi and times 2 pi will give you 8 pi. So I think I should normalize 8 pi squared. I think. No, sorry. No, there's no pi. Sorry. Okay, so then everything okay. Okay, so then somehow from here the entropy and the area of a black hole is already related. You can see the resemblance. Hg. I already G is equal to H bar is equal to C is equal to 1. Okay. I don't like on these constants. Okay, so this is first row, first row, and second row. Okay. Second row is the famous one. The second row is the famous one. The entropy is never decrease. So the second one is the most famous one. Is entropy never decrease. So this is a famous one. And then as you the comparison from here is the of course the area never decrease. Okay. So for the total entropy and total area. So for instance, we already know that the area is of the Schwarzschild black hole is indeed proportional to 4 pi r square, which is the r is proportional to the r is proportional to the mass of black hole. So I just need to be careful about the 4 pi 2gm squared. So therefore, this is proportional to m squared of the mass. So therefore, if the two black hole, anyway, so you guys, so the LIGO has detected the gravitational wave. So the LIGO, what LIGO has detected is that two black holes is just rotating each other, and then eventually, collide them together, and then merge together, and it becomes single black hole. Even though they have angular momentum, but the process is essentially the same. So if the black hole is rotating each other, it just creates a gravitational wave. So it's like if you keep tapping water, so it generates. You keep tapping water in the whatever swimming pool or like a bathtub, it generates the wave, right? It's like this way. So if the wave on the surface of the swimming pool, so it's like if you have the black hole keep rotating each other, then it generates the gravitational wave. Eventually, it merges to the single black hole. So the process, if you look at the process M1 and M2, and it just merge, when they merge together, it becomes, of course, the energy is conserved, as I mentioned over there. So anyway, it becomes another black hole M1 plus M2. Okay. However, again, triangle row is always M1 squared plus M2 squared. Okay, so the area is proportional to the mass or mass square, means that the area never decreases. So we assume, of course, M1 and M2 are greater than 0. So this triangle row should be satisfied. So therefore, area never decreases along the total area never decrease. So this is the second row or some resemble like the thermodynamics of this is the black hole thermodynamics nowadays. Okay. Okay. So then, so this is the black body in Carter-Hawking, and then now Bekenstein-Hawking, Bekenstein appear. So in around also 73. So he asked the following question. So if the black hole is purely geometric object, if you put the hot water inside a black hole, it looked like, so if they do not carry any entropy, but the hot water, of course, is the thermodynamic object, okay, which has entropy. If the black hole is only measured by mass and then the electric charge and the angular momentum and the purely geometric object, if it's just measured, which just characterize a metric in terms of MQJ, then it looks like the entropy decrease. Eventually, they just put the hot water inside the black hole. Just only the mass of black hole will increase, but if the entropy of the black hole doesn't have the entropy, it's just the bio is a second law. So that the Bekenstein proposed a black hole must have the entropy proportional to area. So to preserve, to save the law of thermodynamics. And then the Hawking appears. So we know that the 1 over t, from the first law of thermodynamics, 1 over t is the just derivative of entropy with respect to energy. So this can be understood as 1 over t is and since if the entropy is proportional to the area, you can have so the temperature of black hole is the inversely proportional to the mass of black hole. Okay, so that's what Bekenstein predicted, and then Hawking applied some quantum mechanics on the curved background and obtained the following conclusion. So then Hawking Hawking just showed the following. And I just now introduced all the Kaplan constant. Okay. So this is the what Hawking derived for the mass. So as you can easily see, so the mass of the black hole can be compared to energy of some thermodynamics object, and then if you restore all the constant, you can get this one. Okay? And so therefore, from here, the entropy is indeed proportional to area, and there's a coupling constant, all the coupling constant, C cubed for G H1. Which I didn't do here. So this is the black hole entropy, Hawking, Bekenstein-Hawking entropy. Now let's go Bekenstein-Hawking entropy. Sorry, I misspelled the Bekenstein. Sorry. So Bekenstein-Hawking entropy. Entropy. And this is a place where all the coupling constant, the speed of light and the Planck constant and then Newton constant used. So the C means you need to use special relativity. You you need to use special relativity. And also H means quantum mechanics. All the basic course you learn, so this means you have to use gravity. So we know that if you combine special relativity and quantum mechanics, you need to use a quantum field theory. And then we know the gravity is described classically. Gravity is described by Einstein's theory of gravity, okay? Einstein's theory. But here, to explain this object, you need a combination between quantum field theory and Einstein theory of the gravity, which nobody has succeeded yet. But now, string theory comes to the rescue. For some case of life. And before going to the so that just if you're interested in it, and you can just take a look at the Townsend lecture note. So here you have a Penrose diagram of the short-sheet black hole. This is the horizon, the Penrose diagram. So this is square minus, square plus. So these are spatial infinity, and this is the radius r of the short-sheet black hole, 2GM. This is this is 2GM. So this is script I. This is script I minus spatial past infinity and then the future infinity. And this is singularity r. This is the Penrose diagram. You can use the by-conform mapping of space-time to put like this. And the geodesics are, how to say, anyway, so I'm not going to explain in so much detail. And what Hawking mentioned is that the around the horizon, so this is horizon, what happens is the particle creation occurs. So at the near horizon, so there is the particle creation occurs near horizon, and one antiparticle goes inside, and the particle just moves to the script I. Script I plus. So this is antiparticle. This is particle, or maybe I should use a different color. Maybe. Particle. And then we can just see the really thermal radiation. So this particle, if you look at the spectrum of this particle, you can just see the thermal radiation. This we nowadays call Hawking radiation. Hawking radiation. Which is radiation, which is the same as the thermal radiation. For black hole. Since black hole has the temperature, it's like the sun. If you look at the that's what Planck did, right? If you look at the radiation of the sun, you can just look at the thermal radiation of the sun, which leads to the Planck, find the so-called Planck constant. The same thing happens. Since black hole has a temperature, you should have the I already forgot the thermal radiation depending on temperature. Depending on temperature. So the Hawking just found, apply the quantum mechanics around the car background, and then he has already shown that the spectrum of the radiation obeys really the thermal radiation. So this is Hawking radiation. And then and Hawking asks a very simple question. So if you just put the thermal radiation, then if you put this black hole, your favorite black hole, and then you just put the S wave. You just put the from infinity. You just put the S wave, which is spherical. It's hard to draw the picture, anyway, but you can understand. So that at the spatial infinity, you can put the S wave. Okay, so which is the S wave. S wave in quantum mechanics, which is pure state. Okay. Pure state in S wave is pure state in quantum mechanics. Quantum mechanics. So if you put the S wave into the black hole, okay, which has the interpretation as the pure state, but eventually after Hawking radiation, eventually, so this it will appear at the Hawking radiation. This is the mixed state. Mixed state means that the thermal radiation is really the mixed states of quantum mechanics. In quantum mechanics, it's a really mixed state. So eventually, even if you put the pure state in black hole, eventually after the Hawking radiation, it becomes a mixed state. That violates the law of quantum mechanics. So that's called the quantum black hole information paradox. That's what the Hawking proposed in 1779. So Hawking noticed if his calculation is correct, so this will violate the information, quantum information in quantum mechanics. So this is very simple Gedanken experiment, but this is a major puzzle in quantum gravity. This remains 76. Okay, so to explain this information paradox, we definitely need quantum theory of gravity. Okay? So first of all, so the entropy is defined in statistical mechanics. So microscopic. So we need a microscopic description. So thermodynamics, which is the physics of 19th century, is described by the microscopically described by statistical mechanics nowadays, which is initiated by Boltzmann. And what Boltzmann did is just the entropy, which appear in the thermodynamics, is indeed microscopically log of number of states. So this omega is not chemical potential, but momentum. So this is number of states. And then of course, if you go to the term of the Max Boltzmann, this formula is written, and then now this is called Boltzmann constant. Okay, so So we really need to at least have the insight of information paradox. We really need a microscopic explanation. Microscopic explanation is the black hole entropy. And since the string theory is the theory of the quantum gravity, as I mentioned, emphasized many times, so this G mu nu can be obtained by this a bosonic string. You just apply. What was it? Oh, yeah, sorry. So we know bosonic string. This is tachyonic mode, tachyonic state, corresponds to this. You can quantize the graviton. Quantize. So therefore, why don't you explain this? Replace this quantity by CQ. Can we explain the black hole entropy in terms of log of states that create black hole? So that's I'm going to explain. That was first done by Strominger and Baffa. It's 98, 97. I already forgot. Oh, sorry, 96. As far as I remember. Yeah, 96. For 96. For extreme black hole, there is no temperature actually. So there is no Hawking radiation. So as I mentioned, so Gm square is equal to charge Q, and temperature is equal to 0. Okay? So there are no Hawking radiation. So one of the reasons why this extreme black hole is easy to study is that it's really invariant under the intact under the Hawking radiation, since there is no temperature. There is no thermal radiation because temperature is 0. So it can be stable. If you have a temperature, there is a Hawking radiation. Eventually, energy will disappear. And as you already explained, temperature is inversely proportional to mass. So therefore, as the black hole becomes smaller and smaller, and by Hawking radiation, so the temperature becomes hotter and hotter. So the Hawking radiation becomes more stronger. The effect of the Hawking radiation becomes stronger. So therefore, it's hard to quantum mechanics study the object if the mass of black hole is very small. But however, if the temperature, the external black hole, for external black hole, the temperature is 0, so there is no Hawking radiation. So the black hole is stable. So it's easier to study. So, moreover, so we need to obtain this external black hole, you need a supersymmetry. So supersymmetric black hole. So that's I'm going to explain the second half of the lecture. So let's stop here and take a rest. 10 minutes break. If you have a question. Just if you have a question, just tell me. Okay, so now I wrote another one. I just give it to my secretary so you can help.
但是我们一样，你这里就是保留微分嘛。你不需要保留微分。
Shall we start? Easy. Okay. So let's talk about the block on string theory, Strominger buffer. Before then, I think I just need to mention that the information paradox means in quantum mechanics, time evolution is essentially just Hamilton unitary transformation by e to the I h t. Okay, and the S wave has a pure states. Okay, this is what quantum mechanics tells us. This state is totally different from what the thermodynamic radiation is. That's the meaning of information paradox. Mixed states really sum of all possible states, all possible coming from this temperature. So it cannot be written in like this way by pairs. Yeah. And also just some. Anyway, I can make some comment. But nowadays, this Strominger buffer calculation has done a number of times in a different context. And also recently, the huge development by even. Okay, well, let's start talking about Strominger buffer case. I will make a comment at the end. So Strominger buffer started thinking about forming strings system of strings here. So strong range of alpha starts thinking of a so-called D1, D5, and P system. So features following system. So as I mentioned, so they consider, so D1, D5 means you have to consider in type 2B. P stands for momentum. So you have a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is in 10 dimension. And then you just consider Q1 copy of D1 brane, which sits in here, and the Q5 copy of D5 brane which sits on here. 1, 2, 3, 4, 5, 6. Okay, and then and also here. You just assume this direction is the T4. Sorry, maybe I should call this is T5, which is compactified as S1 cross S1 cross. I mean, which is equal to what am I? Okay. The 5 copy. Okay. So these 5 direction is the compactified S1. Okay. So and then this can be decomposed the T4 cross S1, and this T4 means this 5, 6, 7, 8 direction, this is 9 direction. And now we consider the P stands for momentum, QP momentum. So because of the because it's compactified in S1, so it should have the Kauzak-line momentum. So as I mentioned, so if you compactify a string theory on S1, the open string, that I can move around this S1 direction, the momentum should be quantized due to the Kauzak-line reduction, and then you should have QP divided over QP over R, where radius is R of this direction. This is direction R, and then QP is indeed the integer. So this is called D1, D5 QP system. And then if the number of the so since we now compactify S5, so here, so if you think this T5, if T5 is small enough, the theory effectively reduces this 5D theory. So this is 5D theory. Okay. And if you only look at the low energy effective field theory, so you can just describe the theory is by 5D supergravity along here, okay? Along this direction. And of course, zero direction can be considered as the time direction. And so therefore, so there is some, in terms of this 5D, so just after compactification over this T5, so this 5D perspective, this one is kind of can be understood as some particle moving along, not particle, some object that moving along time direction. Okay? That is exactly the black hole we are going to consider. Some black hole is created by D brane in 5D perspective. It can be treated as a black hole in strong coupling regime of in the string theory. Okay. So what we are going to do is as follows. So therefore, So typical feature of string theory is that so if you take this system, consider this system, if GS the string coupling constant is strong enough, so this object becomes black hole in 5D supergravity. On the other hand, so the GS is very strong enough. On the other hand, if the GS is is weak, strong coupling is weak, the small enough. This has you can use perturbative string theory, string perturbation theory. In particular, so we are going to look at the following place. So here, if you look at the 0, 9 direction, okay? If you look at the 0, 9 direction, so here you have a D1 brane sitting here, and you just look at the 0, 9. If you only look at the 0, 9 direction, so this can be considered as a so-called two-dimensional superconformal field theory. And especially so on x0, 0, 9 direction. And then we can, so if you do this, so you can count the number of states along this regime, okay, in this regime. On the other hand, you can calculate the strong coupling regime. You can use the supergravity description so that you can calculate the area of black hole by using the supergravity description. So now, so therefore, what we are going to use here, right hand side, we use GS is the weak couple string perturbation theory. We calculate we count number of states. Right hand side here, you just consider GS is strong enough. So I think I should write a 1. Strong enough so that the left hand side can be calculated supergravity. That's what we are going to do. And then, so we need a so-called supersymmetry here. Supersymmetry here because the calculation varied. If you have a supersymmetry, calculation is valid all over the region of the string coupling constant, so that you can connect. They can be connected by supersymmetry. So that's the idea. That's the main idea of the Schrödinger path. So if you don't have a supersymmetry, you cannot connect GS's weaker coupling and the strong coupling region. But if you have a supersymmetry, you can connect between them. That's the main idea of the Schrödinger path. So okay, so let's do that. So okay. So how many supersymmetry does it have? The type 2B, 32. So in total, usually 32 supercharges. But if you put D1 brane, it reduces D1 brane. We reduce it to 16. Okay? And D5 brane, which is also reduced by 1/2. So once you incorporate the brane along the intersecting brane, indeed it reduces 1/2. Okay? And then also, if you have counterclockwise momentum, you can have the total in 4 supercharges. In total, you have only 4 supercharges. 4 real supercharges. Okay. Okay. So, and here, of course, we have to assume that the Q1, to create a black hole, I mean, the state has to be heavy. So you have to take Q1, Q5, QP is large enough. It's large enough. So this is what we need to also take into account. So supergravity analysis, so-called membrane. So in supergravity, 5D supergravity. So metric of this system can be written as follows: D is 5 square is minus lambda r to the minus 2 over 3 dt square and plus lambda of r 1 over 3 and the r square. I mean, this one you have to perform lots of computation coming from the supergravity action, and you have to solve again. It's like a Schwarzschild. What Schwarzschild done? So you're given the Einstein action and try to solve the static solution, spherically static and without. Schwarz did it without charge. Here you need to include charge too. But I'm not going to go into detail. Where you have to do the same analysis by studying supergravity action. Where so really these are coming from H1, H5, and K really come from the presence of this D1, D5 momentum system. Where these are really, as you can see, I mean, as we know, the Schwarzschild black hole is something like 1 minus 2gm. It appears something like this one. Right? It's a similar object, but it's in 5-dimensional version. Where the R1, so I mean, and R1 square is given by string coupling constant Q1 and LS to the 6 over V. Oh my goodness, I have to explain what V is. R5 square is GS coupling constant Q5 LS square. Everything can be computed by using radius of string coupling some charges square. So B is indeed, I didn't explain what's B. So you already know LS and then also G coupling constant, GS. So B is the volume of T4. And then R is already I introduced. So R is the radius of the ninth direction of this one. So all the the R1, R5, Rm can be written in terms of string coupling and then string length, which is Rs is equal to square. Oh my goodness. Square root alpha? Which one is correct? Let me, oh yeah, square root. So this one. And all charges and the volume. So this is the solution of coming from supergravity. And then we assume the string coupling, everything, this Q1 is very strong. So in order for supergravity analysis to be valid, you have to consider R1, R5, Rn are all much, how to say, longer than the string length. Okay, so that is the assumption for the supergravity analysis about it. So then, yeah. Yeah, so I think I have to be precise actually. So here, sorry, I think I have to be precise. I've been schematic, so this is not true, sorry. GS is greater than 0 is not true. I think I should take the GS is still small, but the Q1, Q5, QP is very large. Sorry, this is assumption I think I should make to get the black hole solution. Yeah, sorry, this is the, if your GS is string enough, you have to include the string loop correction. So you still, you shouldn't impose this condition. GS is greater than, is the stronger coupling constant. So, and then you can use this metric to compute the 5D surface gravity. Gravity is indeed equal to 0. It's proportional to the Hawking temperature, as I mentioned, and this is indeed 0 as expected from supersymmetry. So it has to be extreme. And then you can just compute the metric of the black hole by using this metric over there. So this 4 times G5 Newton constant. And now, so this area is really come from this the three-dimensional sphere, not the two-dimensional sphere. It's not the 4 pi r square. So therefore, a three-dimensional sphere, the area is given by as follows: 1/4 G5 and 2 pi square. It's no longer 4 pi square r. This is just the r square. So the radius is given by this times this one. The radius given by this one plus radius square, I would say, to the third, and then 3 over 2. So the area of, how to say, area of S3 is 2 pi square r cubed. That's you need to use. You need to use r cubed. So the radius r is r cubed. So here, this times this one, you get the r square, and so you have to use 3 over 2 to get the r cubed. So now everything you have to plug in all these constants. So we already know lambda r is given by this quantity, and then black hole indeed sits on r is equal to 0. So the horizon is sitting on r equal to 0. So the metric diverge GRR equal to 0 at r equal to 0. So what we need to compute is to plug all the constant over here, and then compute the so this is 3 pi square and 4 pi GS square LS to the 8 divided by 4BR. Okay. So to get this one, you need to use the G5. So G5, as you did, you are doing this homework this week? No, you already did. So has to be 2 pi to the 5 volume times R. So the 5-dimensional supergravity here is just compactification of the T5. Okay. So therefore, the 5-dimensional Newton constant is related by the 10-dimensional Newton constant divided by this volume of T5, essentially, volume of this T5. And also, yeah, G 10-dimensional Newton constant is indeed given by, anyway, so this one is just it's written in terms of string coupling constant. This I already introduced a long time ago. But you have to keep track of it. So you can just use this, plug that one into here, and then everything written in terms of the string coupling and the string length and the volume of the 5 torus. And then now here, this one at R equal to 0. So the R equal to 0, this will become the following: R1, R5, and Rm. So, I mean, you have to be careful. I mean, naively looking, you have to plug in R equal to 0, meant to look like diverges. But here you have R squared here. Okay? So you have three copy of 1 over R squared. So that should cancel with 1 over 3, and then R squared cancel with R squared. Okay? Do you understand what you mean? So you have to be careful about how you compute how you compute. I mean, you have to. I mean, naively it diverges, but if you be careful, you can just take a constant term, which is R1 times R5 times Rn. Okay, so this is what you get from this analysis, and then just plug everything, all the constant over here, and that's magically will give you the following. You have to do the calculation, and most of the physicists use Mathematica to compute this kind of stuff. So this is the answer you get. So it's really magical. It's independent of the volume of 5 torus. And everything depends on charges of planes or number of planes. Number of planes. So Q1 is the number of D1 plane, Q5 is the number of D5 plane, and QP is the causal Coulomb momentum, which has to be integer. And I assume positive integer now. So this is what the supergravity tells us, and then and the mass of black hole, I can just write down the mass of the black hole. So 5D supergravity analysis. So mass of black hole is the QP of R plus Q1 R of GS coupling constant plus Q5 RB divided by GS of S. So this is the indeed formula for supersymmetric black hole, supersymmetric extremum 5D extremum black hole. So namely, the mass of black hole is proportional charge of the D brane or number of D brane. up to some constant. So that's the condition for supersymmetric exchange black hole. So that's the 5D symmetry supergravity analysis tell us. And then, of course, what we want to reproduce is the this formula by microscopic count. So now we are going to assume it's as follows. So to see this calculation, to see this calculation by microscopically, as I mentioned, we need to use string perturbation theory. Okay? So string perturbation theory, and also we want to use 2D supercompound field theory, 2D CFT, and to see that we have to assume this 4 torus is much smaller than this radius. Okay, so we assume that this 4 torus to have valid description as 2D CFT, SCFT, we need to assume so we need to assume this one. So the volume of torus is much smaller than this S1. So that the effective description of this different system is coming from this 0 and 9 direction. Okay. And furthermore, we need to, so when the string perturbation theory is valid, GS and also QI is very small. Okay. Here, on the other hand, to this, so maybe, yeah, I think what I should have write is this one. And the GS created GSQI is greatest. That's what we need to do. So then we have the following, the symmetry. So now here you have SO4, sorry, that rotate this direction. So this I call SO perpendicular, and then here you have SO4 parallel to the D fibrane, and then these 0, 9 direction will give you SO1, 1. So these are symmetry of 2D CFT, and in particular this parallel direction, so perpendicular direction to D fibrane, so SO4 perpendicular times SO4 parallel times SO1, 1. So this is the symmetry of this 2D this brane system. And then if you take this SO4, so T4 is very small direction, what we are going to have is the this symmetry, and this will give you SO4 perpendicular is so-called R symmetry. SU2 plus SU2 R symmetry. Am I correct? I just a bit confused. I think I'm telling you wrong. Sorry. Yeah, I think it's okay. Yeah, I think it's okay. So we are going to have is the following. So I want to keep this blackboard. So we are describing the system which is living on this zero. We are going to describe the 0, 9 system, and then so what we have is 2D, so-called n equal to 4,4 supercomponent field theory. And where 4,4 is the you have the SU2 process. Yeah, I hope I'm correct. I may be wrong. 4,4 really come from this R symmetry. Yeah, so it should be correct. Yeah. I'm not convinced. I'm confused. 4,4. No, it should be correct. Supercommon field theory, where the target space, the sigma model space is indeed symmetric. It's orbital space, where low energy sigma model, where the M is symmetric product of Q1, Q5, Q4, which is the, you just consider, so now, so you just consider the following configuration. So you have it's hard to draw. Bunch of D5 ring, QD5 ring, Q5, D5 ring. Okay, and now you have, so this direction is X9, and this direction is X5, 6, 7, 8, and you have a D1 brane, so a bunch of D1 brane. So these are Q1, D1 brane. And we consider the following configuration. You have an open string between them. So open string between them, and then so what the CFT we are looking at, and also of course we can have such a plane, also 5, 5 ring. But we are looking at the string stretch between D1 and D5 ring, and there's the D4 plus T4 and T4. So if you look at the branes that stretch D1 and the Q5, there's the how to say Q1, Q5 choices to take. Okay? So that this T4 comes from this string really can stretch around this T4 part. So it's identified. Where was the choker? So they identify top and bottom, and then it's very schematic, and left and right, and essentially this becomes T4. And this the string between D1 brane and Q5 brane has a freedom to move around this entire T4. Okay, so therefore the freedom really comes from this T4. Okay, and the choice you can make is, I mean, D1 you can Q1 copy of D1 brane. So therefore you can pick one of the D1 branes, so that give you the Q1 choices, and then you can add the other copy of, okay, let me be schematic, the other copy of D5 ring. Okay, so there is in total Q1 times Q5 choices this open string can make. Okay, so in total, so the freedom open string have is Q1 times Q5 copy of 4 torus. Okay, and then you have a symmetric group, Q1, Q5. So you have a permutation symmetry to make it. You have a redundancy. So let's see, Q1, Q5 copy of them, and then yeah. So I mean, you cannot. So there's a permutation symmetry. So 1 Q1 and Q5, and then so you can. There is a permutation symmetry acts on symmetric group Q1, Q5. You can just get rid of this permutation symmetry. So in total, you have to divide by the symmetric group. This is symmetric group. So you know symmetric group, right? Symmetry 1, 2, 3, 4, n is whatever 2, 3, 4, 5, 1, and so on. These are the action of symmetric group. So, but you have to mod out the redundancy by symmetric group. That is called symmetric product. Q1, Q5, symmetric product of T4. T4 is called T4. So at the end of the day, so if you use the assumption the volume of T4 is smaller than S1, the CFD analysis on 0,9 direction is valid, but so in SCFD sigma model. So you have the sigma model description, supersymmetric sigma model description, where target space is really coming from degrees of freedom and the D1, D5 ring open string, D1, D5, 1, 5 ring, dual analysis is valid. Okay. So now we will take so if given us conformability, the first thing you need to do is to compute central charge. And then we already knew that in sigma model bosonic string will give you a central charge 1, and the fermionic state will give you 1/2. So the helpful central charge is number of boson in sigma model. In the 1/2 is number of fermions. That we already know. So, and then, so the bosonic string mod is really coming from, the number of bosonic string is really coming from vibrating transversal direction. Okay? So we know, so already, so let's say 1/5 open string. So let's go 1/5 open string because it's stretched between D1 and D5. So let's go 1/5 open string. So you have number Q1 and Q5, and it can vibrate transversal direction. Transversal direction is 1 to 4. Okay, so therefore bosonic string, the user freedom is 4 times Q1 Q5. 4 coming from this transversal direction, 1 to 4. So you can just vibrate the transversal direction, And then you have a choice of the you make. You can Q1 times Q5. And also, it's a supersymmetry. Boson on the Fermat should have the same number of states. So you want half 4 times Q1 Q5. So this will give you 6 times Q1 Q5. So the central charge is indeed given by the number of d-brane. Number of d-brane. Okay, Q1 times Q5. Okay. And now, so we already analyzed lots of this is torus compactation, and you need to exercise lots of exercise. You have a regular matching condition and so on. So level matching condition for here and minus n bar is given by QP over R. So now we already assumed that the Kawasaki momentum of open string along this S1 direction is given by this QP over R, and then you have a winding mode. And then, so winding mode, and then also you can just have the following, the assumption that the winding is given by Q1 times Q5. Let's see. So this is called actually long string. So here assumption. So this is called long string. It's called long string. So long string as follows. So yeah, let's see. So now, so we just look at that, yeah. So as you already knew that the, yeah, it's hard to explain that. Yeah, it's very hard to explain. Okay, so this can be treated as assumption, but so the last, so the essence is the large d-brane charge limit. So we were going to take limit only long string contribute. Long string contribute. That's the assumption you can make. Contributes. So essentially, what we are doing is that the here. This one is S1R direction. S1R direction, and then the open string is indeed wrapping. Let's see. So this open string wrapping this direction. Yeah, this direction in the in Q1 times Q5 times, so that so it can swipe all the how to say D1 brane and D5 brane. So that is called long string. It's hard to draw the diagram. I don't know how to draw, to be honest. Is there any nice way to draw? I cannot come up. In any case, so Ralph's picture is that you just go, so all the D1 branes stack each other, and just assumption, just go here, and go move to another direction, and move to another D1 brane, and then you do the same thing for another copy of D5 brane. And at the end of the day, what you get is the so-called long string. So it just swipe all the D brane for D1 brane and D5 brane. So that the winding number is given by Q1 times Q5. Okay, so that's called long string, and you have to trust me, and then for large D brane limit, only long string can contribute. Okay. And now we need to consider supersymmetric configuration. Or supersymmetric configuration, which means you have to preserve all the supersymmetry of the four supercharges. All configuration, all states are the ground state in right moving sector. Oh, left moving sector? I call it left or right. Which one is correct? I think I made a left moving sector. Sorry, anti-homomorphic. So which means that you have to be ground state at the anti-homomorphic part. So you have to assume n bar is equal to 0. So n bar equal to 0. So this means the ground state. So this will give you that the n is given by, so right mover is all the excited can be so plug this one into here, n bar equal to 0 means the right mover are all the proportional to Q1 times Q5 times QP. So this is what's going to happen in the analysis for D brane. And now we need to count all the number of states that satisfy this configuration. Okay. So as I mentioned, so we have 4 times Q1, Q5 boson that actually come from fluctuating 4 transversal direction. So that the partition function is very simple. So the partition function we have is only coming from everything, all the left moving sector ground state, and the right moving sector is this guy. Essentially dedicated function with the So you have the 4 degrees of freedom to fluctuate in the transversal direction, and you have the bosonic state which come from 1 over 1 minus q to m, and essentially you get the dedicated function, and this is kind of set of function you have from fermionic states, and you can just do the expansion. And as we know, degeneracy is coming from Q1, Q5, QP system, and the Q to the n. So coming from n. Okay. And then what we need to show is that so you have to count the number of states. So you have to count omega Q1, Q5, QP that satisfy n is equal to this number, this level matching condition. That's what we need to do. Okay. And then you have to use the Cali formula, which is exercise to you guys. So this is coming from homework, but homework, and then if you take the Cardi limit, so we know that the central charge is assumed by what was the central charge is 6 times Q1, Q5. So Cardi limit is the Cardi limit. The central charge is very big. It becomes very big. All charges are very big, and then omega is this is the exercise you have to do in homework. Is indeed the exponential of pi c times energy times 2 by r over 3. So here, if you take the all the charge goes to infinity, the calculation becomes much simpler, and then you have to take a stationary phase, and then you can have exponential So this is the configuration, and then we just plug in the energy or energy or here in this case n. In this case n. So this is a level. So there's a plug that one into here, and then what you get is follows exponential. And then 2 pi times Q1, Q5 QP. Where did I? What was it? Yeah. So C is 6 times Q1, Q5, right? So then you have a Q1, Q5, and then what is E? Where does E come from? Oh, sorry. This is energies, not occupation number. Sorry. I'm sorry. So this E really come from S1 direction. So it should be E is equal to QP divided by QP divided by R. So then everything consistent. Yeah, sorry. So it's a classical momentum. So the 6 times Q1, Q5 cancel with 1 over 6. So which given Q1, Q5, E is QP over R, and R cancels 5. This one. You get this. And then S microscopic is of course log of degeneracy of Q1, Q5, and then QP. And this is indeed just take the just get rid of exponent. You have Q1, Q5, QP. So this is the analysis coming from the deep counting open string coming from deep on the 5 system by using level matching condition and a Cardi form. And this is indeed equal to what we have obtained by supergroup analysis. This is exactly equal to what we obtained as macro coming from supergroup. So that's what the Schrödinger buffer did. In 96. So this was a big surprise when they did calculation. Actually, Schrödinger had an idea to do that. and he found a good crowd like the Balafan to do the CFT calculation. Okay, so this is the analysis you can do string theory so that you can explain the in the black hole entropy coming from supergravity analysis by using the just superconfiguration analysis and counting. Essentially, this is counting states for open string. Okay, so almost time is up. So this is the okay. Maybe I can use it. Any questions so far? So this Cauchy limit is, of course, I just assume all the D-brane charges are big. Q5, QP, all this is Cauchy limit. So this is when this is the case, you can just count the number of states very easily by using stationary phase. That's a homework you have to do. Okay. So there are many development has been done. In particular, so recent years. So this is the analysis coming from. So D1, D5 system. Oh, I already erased, but D1, D5 system. P system really keep you ADS3 CFT correspondence. So now, what we have seen that the CFT2 lives on this x0, x9 direction. And if you take the, so I will explain our next lecture what the ADS CFT means. If you take some nice limit, decoupling limit, this ADS3 part will show up, and then yeah, essentially, you just look at the near horizon limit of black hole. All the metric look like ADS3. And in this analysis, essentially what we did is ADS3 cross S3. That will show up in the, if you take this certain limit. And then, so moreover, if you consider D3 brane, you get the ADS5 cross CFT4, where this is called 4D n equal to 4, 4D n equal to 4 super mLs, or superconformal field theory. And now, so the same analysis can be done for in this case. So recent years, it's a huge development by. So here you can just compute. You can do the microscopic counting here. So-called superconformal index. And here you can again use the 5D supergravity analysis. And then what you can get is that indeed from here, if you do the nice one, it has been a long puzzle to count the correct number of states because superconfiguration index is a trace of -1 to the f e to the lots of j1 plus j2 minus r over 2 times q to the j1. I'm not going to explain what it means. It's kind of supersymmetric index. Here, we just count the number of states honestly, but here for superconfiguration index, you have -1 to the f. So there is a cancellation between Boltzmann and Freeman. But for some nice analytic continuation, one can count number of states of coming from this D3 plane, and if you take coordinate limit, this will give you the Bekenstein-Hawking entropy of coming from supergravity. This one is already it's very recent, about 2000 to 2000 I think 18 or 19. 19. There is 3 group. One is the coming from UK. UK. Samir Mursi, Dario Martelli, and the collaborator. I already forgot. I'm sorry, I forgot the name. So that's the coming from the King's College in the UK. Another group is Kim, and his student, the Korean group, Juno Kim, and Lee, and so on. His student. I already forgot. And also the other group is it's actually Benini. The Sisa, Benini, and his student. The 3 group the slightly different method to count the state coming from for the n equal to 4 superconfirmed field theory, and you can match the 5D supergravity analysis. So even though the Strominger alpha did this calculation for 96, still there are lots of mystery to count this SCFD side, and then to match the supergravity analysis. That's also one the people in researcher in string theory has been doing since 96 already. How many? 25 years ago. Well, we are doing many similar analysis, but more sophisticated analysis you have to do. And another thing here, to match Bekenstein-Hawking entropy, you have to take this Kalle limit. So all the charge is very very strong. Very big. All the D-brane charges are very big. So so that the central charge is also very large. Okay? Central charge is very large. But nowadays, there is so-called supergravity localization, supersymmetric localization, and so on. One can somehow take the finite D-brane charge Q1, Q5, QP. Even supergravity analysis goes one loop determinant and so on. One can just extract the information about. So as I mentioned, for this analysis, supergravity macroscopic one is just only can be obtained coming from GS QI is very strong coming from supergravity analysis. But if you use some supergravity on supersymmetric localization on supergravity, one can extract the information of the even finite Q1, Q5, QP system. And so that you can match with the for how to say CFT side you can count any number of states. You don't need to take the large D-brane charge limit. But supergravity side is very hard. But nowadays you can do a little bit of finite D-brane charge in some nice settings. So that's the recent development we made. Okay, so let's stop here.